Another set of theorems that are going to be important for finding the zeros of a polynomial function are the fundamental theorem of algebra and the number of zeros theorem. The fundamental theorem of algebra says that every polynomial function of degree n is greater than or equal to 1 has at least one complex zero. And then the number of zeros theorem says that every polynomial of degree n has n complex zeros provided each zero of multiplicity greater than 1 is counted accordingly. Like if a factor, for instance, has a multiplicity of 3, that means we already learned that that zero is not unique. It occurs 3 times, right? The function passes it 3 times. And so we want to keep that in mind when we start to find the zeros of our polynomials, that the degree of the polynomial, which again is the highest power, tells us how many zeros there are, although those zeros may not be unique due to the multiplicity of the factors, right? So whenever you have a higher multiplicity, that means that that factor is repeated and it's not a unique zero that corresponds to that factor. So we have this problem here. We want to solve the polynomial equation in the complex numbers. We have c of x is equal to 3x to the fourth minus 7x cubed plus 6x squared minus 28x minus 24. Now we have a few more theorems to go over to help us with this. One is Descartes' rule of signs. We let f be a polynomial function with real coefficients written in descending order. So that just means that the powers on the terms are written in descending order. So you have your highest power first and you go down from there. The number of positive real zeros of f is equal to the number of variations in sign of f of x, or is less than the number of variations in sign of f of x by a positive even integer. If f of x has one variation of sign, then f has exactly one positive real zero. The number of negative real zeros of f is equal to the number of variations in sign of f of negative x, or is less than the number of variations in sign of f of negative x by a positive even integer. If f of negative x has one variation in sign, then f has exactly one negative real zero. So let's go ahead and apply Descartes' rule of signs. So we're going to first look at 1. We're going to find the number of positive real zeros of f. So for this one, we don't have to change the polynomial at all. We're just going to look at the polynomial c of x and just look at sign changes between terms. Notice that here we changed from positive to negative. Here we changed negative to positive. And this is positive to negative as far as the signs that we have here. And then there's no change here. We have a negative and a negative, so there's no change. So there's only 3 sign changes. Since there are 3 sign changes between terms for c of x, there are 3 or 1 positive real zeros. So that's what we mean here. It says the number of positive real zeros of f is equal to the number of variations in sign of f of x, or is less than the number of variations of sign of f of x by a positive even integer. So it's either going to be 3 because we had 3 variations in sign, or it's going to be 3 minus 2, which is 1 positive real zero. And the reason we take out 2 goes back to what we just learned about here, the complex conjugate pairs theorem. If it's not a positive real zero, then it would have to be a complex zero. And those complex zeros only come in conjugate pairs. So that's why it doesn't say 3 or 2 or 1. It either has 3 or it has 1, because you're taking away 2 that are going to be a conjugate pair of complex zeros with imaginary components. All right, so we have 3 or 1 positive real 0. Now, let's find out the number of negative real zeros of f. So the number of negative real zeros of f is equal to the number of variations in sign of f of negative x. So we want to count the number of variations in sign of c of negative x here. Now, that means that we need to run a negative x in here. So notice I did put this in here. Now, it's pretty simple to simplify this. You have negative x to the fourth. If I take a negative and I raise it to an even power, it becomes positive. So 3 times negative x to the fourth is just going to be the same as 3x to the fourth because it becomes positive. Here I have negative x cubed. Since it's an odd power, it's going to stay negative. Well, I have a negative here and I have a negative. Negative times negative makes positive. So this is positive 7x cubed. And then this negative x squared, that negative, since it's an even power, is going to become positive. And so I have plus 6x squared. And then I have a negative x here times negative 28. Negative times negative makes positive. And then we don't change this negative 24. There's no x with it to run the negative through. So if you notice here, we only have one sign change, right? This is positive to positive, positive to positive, positive to positive, and then we have positive to negative. So only one sign change. Since there is one sign change between terms for c of negative x, there is one negative real 0. And it says that here on the theorem. If f of negative x has one variation in sign, so that's a sign change, then f has exactly one negative real 0. So this is going to help us when we want to narrow down our possibilities for zeros. So we know there could be 3 or 1 positive real 0, and then we know there's 1 negative real 0. Now, do you notice that this polynomial c of x is a higher power, so we don't really have a nice formula like the quadratic formula that we could use for a power of 2 to help us break this down. We've got to use a lot of different techniques. So the following theorems are going to help us break down this polynomial. So let's go ahead and look at those theorems.